welcome to PASC26. This is the highlights from the mini symposia. I'm here with the organizers of two different mini symposium, but always still on plasma fusion and nuclear fusion. The first mini symposium is applications of AI and machine learning towards addressing magnetic fusion challenges. And the organizer is Stefan Brunner from EPFL. And the second mini symposium is computational methods in optimization and modeling of stellarators. And this is organized by Florian Hindenlang from the Max Planck Institute of Plasma Physics, Germany. Sorry, I needed to read it too long. The titles are too long to remember by heart. So the obvious first question is for both of you, so you decide who starts. What did you want to address when you submitted this mini symposium at the PASC conference? What were the triggers or the expectation that you had? Maybe Stefan, you start.
Well, plasma physics, nuclear fusion is a very complex problem to address. We deal with a multi-scale system, and high-performance computing has always been key in understanding these systems. And the most detailed description, the first principle description, are kinetic simulations, but they're extremely costly, and in practice, it's too costly to carry out, to address many problems, so we make use of a hierarchy of reduced models, and we always have to carefully balance accuracy with efficiency. And in recent years, AI and machine learning has appeared as a very attractive alternative to traditional approaches to reduce models. So that's
some of the computational simulation to reduce the computational cost. Sure. And for you?
Yeah, in our case, it was more application-driven. So the stellarators are something that is still on a, let's say, not that high fidelity side. It's really hard to model them because they're three-dimensional objects. Tokamaks have been studied much more into detail. But also for stellarators, it's interesting because of that. Right now, even the state of the art would be that you are still don't know how a stellarator really should look like. So you know how a tokamak should look like, but stellarators have so many different shapes that we're still in the exploration phase.
But then very shortly, what is the difference from a tokamak and the stellarator?
Well, first of all, the tokamak is an axisymmetric device, so it looks like a donut. Yeah. And the stellarator is defined as being non-axisymmetric, so it can be anything that does not look like a donut. So maybe that's the shortest answer.
Okay, but then, I mean, you mentioned the computational cost, I suppose, is one of the challenges. But what are the challenges really that the plasma physics is facing now? And that you also try to address with your mini symposium. Besides, I mean, you mentioned you want to use AI, machine learning, Stefan, in your case. But what are the challenges there?
In machine learning, well, there's maybe one should talk already of successes, and specifically at our lab, we were able to achieve experimentally, thanks to machine learning techniques applied actually to real-time control plasmas shapes that we always dreamt of doing before, but with traditional feedback techniques were not achieved. But now, working actually in collaboration with DeepMind, they achieved so-called doublet configurations where two plasmas are achieved simultaneously and connected, and so there's a lot of promise in all this, but maybe when it comes to machine learning, truly understanding the limits and the reliability of machine learning tools when you design a reactor is still something that has to be very much worked on.
And understood, yeah. And for you, what are the next the most pressing challenges?
I mean, one thing it's as I said, it's in the mini symposium. It was algorithms in the optimization loop. So the optimization loop obviously needs codes that are fast, and we're trying to push obviously the higher resolution cases into the optimization, and then we need to do this in a parallel computer. We need to couple all of these things. It's not just one model that we run, but we have multiple things that we evaluate on the equilibria, for example, and things like this. That has to work all together. And there has been tremendous work now on Python frameworks and things like this, and that was really a big change because I think in tokamaks, again, there are already frameworks existing that do control or do these things, but in stellar optimization, because it's just such a vast space, you need to do completely different tools, and many are individually very good, but then they're not fast enough, or they're not...
But the tools that you're using for the stellarator, now I comes from the experience of CSES, are they able to use accelerators, so GPUs?
Some of them nowadays are. They even use automated differentiation. That was a very interesting topic in the last year, because that's coming up much more, and I think we will see of that. We will see a lot, also because the machine learning actually drives the development of automatic differentiation, and that helps our development, because when we do optimization, we obviously want to know gradients and things like this, and really would be great to have more auto-diff basically in the different codes, and that's a challenge because many codes are still not ready. So we are still on the verge of
okay, but that sounds promising. My last questions for both of you. So now you have had your mini symposium at the PASC conference. You had a lot of discussions and maybe gained some momentum. What would you like to see happening? What are the next steps that you would like to see happening, maybe in the next few months or 1 year until next PASC conference?
In general, or in?
In general, I mean, after the discussion that you have been having here at CSES, of course, in general, you can also, if you like.
One thing that I would really like is that people come together more often in these topics. Okay. So the groups are spread around the world. We had a very good collaboration from the Simons Foundation for the last, I think, 8 years, and that was really a boost in collaboration. And now all the international conferences. Yeah. So my wish actually is that we try to work much more together, because that's where progress is made, basically.
Usually, yeah. Working in isolation is never the path to success, or it's much slower. Let's put it this way. Yeah. Stefan, for you?
Well, I just say a good thing about the PASC conference. I've participated over many years, and it's always a great venue, getting together the scientists, the physicists in our case, and the applied mathematicians, the computer scientists. And this year, again, we had very good interactions. It's fostered a lot of ideas, and it strengthened collaborations as well. So
that's it's really in the spirit of the PASC conference. Well, you all know we are all looking forward to see the fusion nuclear plants, because alternative source of energies are a must now more than ever. So absolutely. I really wish you good luck in your research, and perhaps I will see you again next year at the next PASC conference. Thank you for joining us.
Thank you.
Thank you.